Hello and welcome to TidyX episode 171, TidyX's screencast where we go through and explain how our code works. My name's Ellis Hughes.
And my name is Patrick Ward. Thanks for checking in with us at TidyX. As always, be sure to like and subscribe on the bottom there in the YouTube channel so that we get your feedback, get your information, get your questions answered. Also, if you enjoy the work and you enjoy the show, we do have a Patreon page, and we're happy to accept any donations that you would like to make. That said, we are going to jump into episode 171. We've gotten a lot of positive feedback from these sort of micro episodes where we say something in 20 minutes. And so we've done a few of those, and people seem to really like them. So we're going to continue on this week. We're going to do Bayes regression in 20 minutes.
Learn all you need to know about Bayes in 20 minutes.
Keep it to 20 minutes. It won't be all you need to know about Bayes. It won't even be scratching the surface, but it'll be enough to give you some information to sort of get you going.
Yep.
So we have a few key packages that we're going to run here. Tidyverse for your data manipulation and visualization needs. Bayesplots and tidybayes are just sort of helper packages for us to plot and visualize Bayesian models. Broom mixed is just an extension of the Broom package, works more with mixed models and works with Bayes models where we can get the outputs in a nice and tidy and clean format. And then finally, the workhorse, the engine of this script is going to be rstanarm, which is basically a wrapper for Stan. Stan is a coding language for building Bayesian models. It's an entirely different language on its own. You can run it from the R console with rstan. You can run it from Python with pystan. But rstanarm is one of two that I know of, packages, BRMS being the other, that are wrappers. And what they do is they take the common conventional regression type syntax that we'd see in Bayes, and they say, okay, if that's what you want to do in Bayes, we're going to go ahead and we're going to code that all in C++ under the hood, and we're going to create the Stan output for you. And so they make this very convenient. So that's what we're going to be using.
Yep.
Data, mtcars, super simple. Pull it in. We've got our data set, and we've seen this data set a billion times. And we're just going to build all the good stuff. We're just going to build a simple linear model. So normally in Bayes R, we would just do LM, right? And we'd have this nice little linear model, and that would give us a cool output that we could interpret. If we're in rstanarm and we say we want a Bayesian model, all we're going to do is do stan, GLM. And you can see it ran our 4 chains of our Markov chain. Now, there's a number of arguments that go inside of this that we're not going to get into today because we're trying to do Bayes in 20 minutes. So things like how many chains do you want to run? Things like specifying your priors on the intercept or on the slope coefficients. We're not going to get into that. We're going to use rstanarm's default priors, which are weakly informative. And so all that to say that they allow our Markov chain Monte Carlo to explore the parameter space within the default priors, and they're very wide, and we'll show you what they are in a second. When you type print and you put the model name inside, we get this very convenient looking output. You could also just type fit Bayes and you'll get a similar type of output. So if you type fit Bayes right there. Yep.
Boom. Oh yeah,
you get that output. Or you could type summary, and summary gives you a little bit additional information as well as the model coefficients. Yeah. So it gives you things like your R hat values and your NF values, which are useful for checking model convergence. But again, we're not going to get into that today. But those are just ways that you can look at the models. The other thing you could do is get your credible intervals. So this is not undifferent than if we had a linear regression model and we typed confint and we got the confidence intervals. And here we're just getting our credible intervals. So we have our estimates and our standard errors that we saw in the print function above. And then we have our 90% confidence intervals for those coefficients. Mm-hmm. If we want to know what the priors were, because again, we didn't specify our own priors. We basically said, hey, rstanarm, use the default priors. It's safe. And so we can see the location, which is the mean, and the scale, which is the standard deviation. So our coefficient priors, for example, are on the scale of 0 and 2.5. And so the The data is getting scaled in the back end so that it's on a, if you think about it like a z-score, like a normalized scale with a mean of 0 and a standard deviation of 1. And then we're saying, go ahead and enjoy investigating the parameter space from 0 to 2.5 on the during the Markov chain. So that's what we have for our priors. And then those are the priors on the intercept, the coefficient, and then the auxiliary is the prior for our sigma, or for the error term within our model. Or if you're in regular regression, we'd call it the residual standard error. You'd see that error term at the end of the data set. We can look at how well the model converged with the trace plot. So this is going to run our so if we run that, we have our 4 chains, which we saw when we ran the model. It kicked out that huge output of 4 chains that we're running. And this is just at each turn of that Markov chain, how the model's exploring the space and before it converges. And we have a number of Bayes episodes that we've done in the past where we called these the fuzzy caterpillar plots. These are nice to see. We can see that we don't have any sort of errors here where the data is becoming biased, or it's taking off in a different direction, or it's minimizing really small, or something strange is going on.
Yes,
exactly. So that's one way to look at how well the model, the Markov chain worked. Another thing you can do is actually plot the densities of the different chains for your coefficients. So here's just our typical normal density plot of the coefficients. So we can see each of the 4 chains, and we can see that nothing weird is going on here where one of the chains is super off the wall compared to the other 3. So generally, it looks like the model has converged around something that it believes to be the coefficients and then the sigma, the error term for this data. So it's generally converged around this. And then finally, we can look at, if we run this one, go ahead and hit that. And this is just going to give us the actual check, the posterior predictive check of the data. So the blue line, thick blue line, is the actual weight here for the, in the observed data. And all of those little thin ones are the different Markov chain outputs. So you can see we're generally capturing the data. Maybe some of them are a little higher and some of them are a little lower. But we'll see what that looks like here in a second when we pull out the posterior distribution of the data. So in order to get the posterior, so remember, we have these 4 chains. We ran this Markov chain and we said, hey, when we look at this data and we explore the parameter space, we have all of these potential options of models that could have fit this data. Whereas if we did LM and we looked at just the frequentist version of linear regression, like in Bayes R, it would give us one single model, right? And that's in frequentist data, in frequentist world, that's what's considered fixed. So they consider those parameters to be fixed and the data moves underneath it. In Bayes, everything is totally open to uncertainty. And so look, if we pull this out, what we have is I believe called the DIM. I think it's what is it, 2000? I think it's 2000, 4,000.
Because
sorry, yeah, 1,000 per
each Markov
chain.
have 1,000.
Yeah. So we have 4,000 rows of potential intercept and slope and error terms that could have fit this data. And that's why if we look at that right plot, those blue lines are all representing the different potential distributions of weight, the different potential slope and intercept models that could have fit this type of data set. So we can investigate this further. For example, we can plot the entire distribution of those 4,000 draws from the Markov chain. And that's kind of nice because now we see that instead of having a single point like we would with frequentist regression, where maybe weight coefficient would be negative 5.25, we have a whole distribution of options, which allows us to calibrate our uncertainty about this data. It's not one thing, it's many things. And if you're in the business of making decisions, you want to be able to wrap your head around that uncertainty, because very infrequently in life are things down to one single point estimate, right?
Yeah. You've got to take a lot of different pieces of information together and try to assess how likely is this prediction going to actually happen.
Correct.
Or what are the upper and lower bounds of...
Or we can use the distributions there to calculate integrals. So we can say, how much probability density is under the curve above, let's say negative 0.4, and maybe that's like 3%. And we can say, well, what's the probability of a weight coefficient being above negative 0.4? Might be 3% if we're looking at it from a probabilistic standpoint. We can summarize these. So if we summarize these with the apply function, so we're just going to take the 4,000 draws and we're going to go column wise, and we're going to ask for the function being the mean and standard deviation. We're literally going to get back, return to us, the slope and the intercept that we saw when we did print fit Bayes. Those are the same values. So because all we're seeing, so if we type print fit Bayes, or we just type fit Bayes in the console, and we hit enter, those values are the point estimate summaries of these entire distributions that we see in the plot. So that's kind of cool, right?
Yeah.
The summary output is producing these, providing us, the summary output is providing us with the point estimates of our model, but we know that we have all of this inherent variability within that model that we can play with. So let's see what else we can do with this data. What if we scrolled, what if we took this data and we summarized it by some credible intervals? So now we just pivot the data longer and we say, hey, let's look at some 90% credible intervals. Oh, there we go. I think it wants you to use reframe because it's
now.
A newer version of yeah. So
yeah.
There you go. So now we have credible intervals. So we have the percentile, we have the 5th percentile, the 50th, the median, and then the 95th. Okay, that's kind of cool. What else can we do? We can take these 4,000 distributions and sample. So we're going to slice sample 10. So we're randomly going to draw 10 of the 4,000. Remember, these are 4,000 potential intercept lines that could have been generated from our data. We've extracted only 10 of them at random, and we're going to plot them over the data. So go ahead and plot them. And what we get is we get a look at those 10 of the 4,000 potential intervals. If we plotted all 4,000, we would get something that looks like the geom smooth confidence interval, right? We could plot more, and we're going to see how it starts to fill in. And again, this looks like if we were to just type geom smooth and ask for the standard error equals true, we would be able to get a confidence interval return back. I think you did. Well, if you typed a method is LM, but yeah, but you get the idea.
Yeah, exactly.
Okay,
let's call it off there real quick so that we can go on to the next pieces.
We can also make some predictions. So what if we wanted to make a point prediction? Let's say we had a new car pull into the shop with a weight of 3.2, and we say, gosh, what do we think the miles per gallon is going to be? If we want to make a point prediction, we can use the handy predict function, which we've used before, and we think that miles per gallon is probably somewhere around 20.2. What happened when we use this prediction function? What actually happened with this? Let's think about it like this. We're really just running the regression model. So if I run coefficient fit Bayes 1, I get the intercept. And if I get the coefficient 2, I get the weight. And so basically all I'm doing is I'm using that linear equation model for a line, and I'm saying intercept plus weight coefficient times weight produces 20.2. It's the exact same value. What if we want to expose some of the uncertainty around this? Well, rstanarm has this handy function called posterior linear prediction. And we just put the model in there and we say, hey, we have this new data. And what does this give us? It gives us thousands. It gives us 4,000 potential outcomes. Remember, when we pulled out the 4,000 rows of the 4,000 rows from our Markov chain, it's basically a prediction from each of those rows using that same equation I used above. We can summarize this with a histogram. We could summarize the mean and the standard deviation and the quantile intervals. We can also get the posterior interval. So great, we've got a lot of information to play with. Again, how did this work? Let's do it by hand. So now, instead of calling fit Bayes, I'm taking the 4,000 random draws and I'm saying column 1 is the intercept, okay? And I'm saying column 2 is the weight coefficient, and multiply column 2 by our new data, which I just repeat the 4,000 times, 3.2 repeated 4,000 times. If I run this, what do I get? I get 4,000 potential miles per gallon, when I plot the histogram, I get the exact same histogram that we saw from posterior linpred. I get the same mean, I get the same standard deviation, and I get the same quantile intervals. Now we just did it by hand. So when you use these functions, this is what's going on under the hood. The last piece of information that we might want to bring in is
So,
that model error.
so to
Yep.
say, like this is saying that on average we'd expect a car of 3.2 tons to be on average 20.17 miles per gallon, but our model is saying, but there's a little bit of fuzziness in that, so they could go down to 19.2 or up to 21.1 based on this data that we've seen.
It's saying on average, a car that's 3.2 tons, the average car will be somewhere between 19.3 and 21.1 miles per hour. But let's say a new car comes into the shop. In order to take the information about that new car, not about the population, what I just said is a statement about the population, the average car.
Mm.
But if we're talking about one specific car, we have to incorporate the model error, that sigma, into this data. And so one of the ways that you do that, this is the difference between a confidence interval and a prediction interval. We're going to do that right now.
Did not
Our,
try to cue that up.
what's that?
Did not try to cue that up. That was
Yeah,
an
but you
honest
did.
question.
That was good. The function within rstanarm is posterior predict. So now we're using posterior predict. We use it the same way as the predict function. And again, we get returned back to us a whole 4,000 string of possible values. So watch. Now run the histogram of this. And boy, we have a lot more uncertainty, right? Because the model error, the model sigma, adds additional random noise to our prediction. Okay.
Mm-hmm.
So now, yeah, if we run that posterior interval. So now what happened under the hood? Okay, let's see what happens here. So we can obtain these results by hand. So we grab our sigma value. So yeah, we simulate, we create a n of 4,000. We grab the sigma value. So that was the third column in our Markov chain. This is the error. So like on average, we're off by about 2.7, 2.5, 4.1, 2.5, 2.6, 3.1, 3.0. We're going to make this prediction the exact same way. Yeah, hide the last plus sign there. This is the exact same thing we did above. We took the 4,000 rows of our Markov chain intercept, the 4,000 rows of our Markov chain slope coefficient, and multiplied it by the 4,000 weight, 3.2 repeated 4,000 times. Now, scroll over, we're adding some random noise that represents the error. Remember, the error in a linear model is believed to be normally distributed with a mean of 0 and a sigma. In this case, the sigma is from our model, which is our 4,000, each of those for one individual regression model. We're going to just borrow that sigma, and we're going to say the mean of 0 and standard deviation of sigma, and we're going to throw that error in. So when we run this, we're going to get a histogram that is going to be much wider. It's going to look like it was above. Whoop. Oh yeah,
The window is too small.
So now we calculate our mean and our standard deviation and our predictive intervals, and we say the 3.2 ton car has a probability of weighing somewhere between 4.9 and 25.7, having 4.9 and 25.7 miles per gallon. That's relatively large, but this is a simple linear regression. If we had other information to build into this model, we could probably shrink some of our uncertainty around the miles per gallon. So we could add additional variables.
No, not MT.
Drat.
What?
Drat, D-R-A-T.
Yeah. You can
cylinder.
build this all out, but
you can build it out.
Does this all for us, so we can just quickly go, oh, what's going on here? What would be a good posterior interval? So now with this this new information, oh no, I'd need to do it on that one. Oh, because yeah, I need.
Oh, you didn't have a new
data.
Yeah, you need a new data, so you'd have to randomly pull out a row or something. Yeah. Meh.
But anyway,
that is basic Bayes in 20 minutes.
Basic Bayes in 20 minutes, everybody. There you go. Thank you all for joining us for another very quick episode of TidyX. Hopefully you learned something. Leave a comment down below if you want to hear more about another topic. If you want us to go into more Bayes, if you want us to go into more like data viz and using ggplot or some other techniques, let us know what you want to learn in the next 20 minutes of your life. Cool? All right. With that, thank you so much for joining us. As always, my name's Ellis Hughes. You can find me on various social media sites at Ellis_Hughes.
My name's Patrick Ward. You can find me on X at OSPPatrick at tidy_explain is where the screencast lives on X. Of course, YouTube is the easiest way to get in touch with us. Like, subscribe, drop the comments down below. We do have a Patreon page if you'd like to donate to the show. We're appreciative of anything that you would like to give.
Thank you all so much, and keep on exploring your world.